Hi and welcome to Broke Abhiyantrics. So today again we are going to solve a couple of problems to talk about the effects of uh, Hooke's law and the stress strain. Most probably we'll be concentrating on volumetric strain and the change of volume of a particular material. So with these topics in mind, let us start talking about the first question. So which is a steel cube of volume 8000 cc. So let me just change the color of my pen here. So I'll just go with yellow. Okay, so here the initial volume is given as 8000 cc. Is subject to a all around stress of uh, 1330 kg per centimeter square. Okay, so the bulk modulus of the material is given as 1.33 into 10 to the power of 6 kg per centimeter square. So since all the units are in centimeter, I'll just keep that in mind. I'll not change it to meter cube or millimeter square. Let me start solving the question. So the modulus of bulk modulus is given by the all around stress divided by the volumetric strain. Right, so here the volumetric strain, I don't know the value, I'll just calculate the volumetric strain. So which is nothing but the overall stress is 1330 kg per centimeter square whole divided by the k, that is 1.33 into 10 to the power of 6. So this gives me the answer 10 to the power of minus 3. Now volumetric strain is nothing but change in volume divided by the original volume, which is nothing but 10 to the power of minus 3. The original volume is given as 8000 cc, so the change in volume will be equal to 8000 into 10 to the power of minus 3, so which is nothing but 8 cc or 8 centimeter cube. Right, so a fairly very simple question. So let me move to the next one. So here, okay, a bar of uniform cross section is subject to an axial tensile load such that the normal strain in that direction is 1.25 mm per meter. Okay, so if the Poisson's ratio of the material is 0.3, the volumetric strain. So they've directly asked me to solve the volumetric strain. So let me just draw a schematic just for our understanding. So we have a bar, so rectangular bar. Okay, so I'll just name it as L, and I'll take this as B, and I'll just take this as the depth. Okay, so with this in mind, so we'll have to calculate the volumetric strain. So we know that volumetric strain is nothing but the volumetric strain in x direction plus volumetric strain in y direction plus volumetric strain in z direction. Right, so here now if I want to convert this all of the other direction into the longitudinal direction, I'll have to make use of the Poisson's ratio. Right, so the Poisson's ratio is nothing but the lateral strain divided by the longitudinal strain. So here if I consider the x direction as the longitudinal direction, so I'll just have to convert this to strain into the longitudinal direction, so which is nothing but, so here the lateral strain would be equal to Poisson's ratio into the longitudinal strain. Right, so here, so I'll make use of this, and now they have said that this particular prism bar is in tension. Right, so if this is in tension, the longitudinal strain will be elongated, the bar will be elongated in this longitudinal direction, and this will be in compression. Right, so these D and the B value will be getting reduced, only L value will be in positive. So meaning that delta L will be positive, delta B and delta D will be negative. So with this in mind, so I'll consider these directions in this formula itself, so that I'll be having epsilon x. So here instead of epsilon y, I'll be writing it as minus nu into epsilon x plus, sorry, again minus, because we have only one load, minus nu into epsilon x again. Right, So here epsilon x is nothing but epsilon L, that is change in the longitude or the change in length divided by the original length. So that is given as 1.25, right? So here I'll have 1.25 minus 0.3 into 1.25 minus 0.3 into 1.25. So which is nothing but 0.5 mm per meter. So this is the volumetric strain of this particular prismatic bar. Okay, so let me move on to the next question now. Alright, so here, so for elements shown in the figure, find the linear strain in x, y and z direction and also find the volumetric strain. So I'll have to find out epsilon x, epsilon y, epsilon z and epsilon v. Okay, so now just remember the sign convention. In the sign convention, the tension will be always positive and compression will be always negative. So I'll make use of this. So here sigma x, so the total stress in the x direction would be 2 sigma, so this is positive. In y direction it would be minus, so I'll use this directions, right? So this is x, y and z. So in y it is going to be minus sigma, and in sigma z it is going to be minus 1.5 sigma. Okay, so with this in mind, let me just go to the strain in x direction. So strain in x direction, so which is nothing but epsilon x will be equal to the longitudinal strain or the normal strain, so which is nothing but epsilon or sigma x divided by E, right? So again there's also going to be changes in B and D like we did in the previous problem. So again I'll have to convert this lateral strain in the y and z direction because of sigma x. So I'll be having that in respect to the with help of Poisson's ratio I'll be converting that. So we'll be having something like minus nu into sigma y divided by E minus nu into sigma z divided by E, right? So this would be the total strain in the x direction because of sigma y, sigma x and sigma z, right? So here this is going to be the normal strain, so these two will be the lateral strain in x direction, right? So with all of this in mind, let me just substitute the values and we'll simplify this. So sigma x is nothing but 2 sigma divided by E plus nu into again y we have minus into minus, we'll be having plus into 1.5 sigma divided by E, and again for the z this is z, I'll just write it as sigma nu, again minus into minus, again I'll have plus nu into 1.5 sigma divided by E. Okay, so if I simplify this, let me just take sigma by E as common. So I'll have 2 plus 1.5 plus 1, again plus 2.5 into nu. So this would be epsilon x. Okay, so again strain in y direction, right? So again I'll call this as epsilon y, so which is nothing but sigma y divided by E, again minus because of the stress in other directions, minus nu into sigma x divided by E minus nu into sigma z divided by E, and again just substitute the values. Sigma y is nothing but minus sigma divided by E, and again sigma x is positive, so I'll have minus nu into 2 sigma divided by E, and again sigma z is negative, so minus into minus I'll have positive nu into 1.5 sigma divided by E, and again if I take minus sigma by E as common, if I take this, so I'll be having 1 2 minus 1.5, again I'll have 1 plus 0.5 nu. Okay, so this will be epsilon y. So again, strain in z direction, so which is nothing but epsilon z will be equal to sigma z divided by E minus nu into sigma x divided by E minus nu into sigma y divided by E. So again, this will be equal to, if I substitute, so minus 1.5 nu sigma divided by E minus nu 2 nu sigma divided by E, and again plus sigma nu divided by E. Now, and if I simplify this, epsilon z is going to be minus sigma by E into 1.5 plus nu. Okay, now volumetric strain. So epsilon V will be equal to epsilon x plus epsilon y plus epsilon z. So if I add all the changes or the strains in all three directions, I'll be getting the total volumetric strain, right? So which is nothing but sigma by E. I'll just skip one step here. Sorry, I'll just substitute 2 plus 2.5 nu minus 1 minus 0.5 nu minus 1.5 minus nu. So if I simplify this, I'll be having sigma by E into minus 0.5 plus nu as the answer, right? So so this is how we'll calculate the different changes for a prismatic bar if it is a tri-axially loaded element. So I think I'll just take few minutes to talk about different shapes of the elements of different shapes, right? So for a cylinder, right, so the volume of a cylinder is pi by 4 into d square into L. So this will be the original volume, and the change in volume delta V will be given by the formula pi by 4 into d square into delta L plus L into d into 2 delta d, right? So again, so totally epsilon V will be equal to epsilon L plus 2 epsilon d. So for a cylinder, and again for a sphere, the original volume will be pi d cube divided by 6, and the change in volume will be equal to pi by 6 into 3 delta d, 3 delta d into d square. Alright, so epsilon V volumetric strain will be given by the formula 3 epsilon d. Okay, so let me just move on to the next problem now. Okay, now a plate 2 meter into 2 meter into 20 mm is subject to a stress of sigma x is equal to 100 megapascal tensile stress. Okay, and sigma y, sigma is missing here, sigma y is given as 50 megapascal. This is compressive in the plane of the plate. Okay, so modulus of velocity of the plate is, let me just write it down, sigma x is given as 100. So if it is in millimeter square, so I'll keep all the dimensions in millimeter square, so I'll have 100 Newton per mm square. So sigma y will be equal to, compressive is minus 50 Newton per mm square. Okay, so in the plane of direction, so I'll have g as 200 into 10 to the power of 3 Newton per mm square. So the Poisson's ratio nu is given by 0.25. Calculate the change of volume, so delta V we'll have to calculate. Okay, so now let us start with a simple formula, and also the length is given, length is equal to breadth, that is equal to 2000 mm, and the thickness T will be equal to 20 mm. Okay, so with this in mind, let us start solving the question. So volumetric strain. So volumetric strain for cube will be given as sigma x plus sigma y plus sigma z whole divided by E into 1 minus 2 nu. Right, so if we substitute in this particular formula, so sigma x is 100, sigma y is minus 50, sigma z is 0 divided by 200 into 10 to the power of 3 into 1 minus 2 into 0.25. Okay, so 0.25 into 2.5, 1 minus 0.5 is 0.5. So if I simplify this, the volumetric strain would be something 1.25 into 10 to the power of minus 4. Right, so again volumetric strain is given by delta V divided by the original volume. Right, so here I'll have to find out the delta V. It means that delta V is equal to epsilon V into capital V, so which is nothing but epsilon V is 1.25 into 10 to the power of minus 4 into the original volume of the cube is 2000 mm into 2000 mm into 20 mm. Right, so which is nothing but, so if I simplify this, delta V will be equal to 10,000 mm square, sorry, mm cube. Right, so let me move to the last question now. Cylindrical bar of 20 mm and the length is given as 750 mm. During a tension test, longitudinal strain was found 3 times the lateral strain, 3 into epsilon L. So epsilon L divided by sigma is will be Poisson's ratio. So Poisson's ratio is 1 by 3, so that is nothing but 0.33. Okay, so calculate the rigidity modulus, so that is G, and we'll have to calculate the bulk modulus, that is K. If the elastic modulus is given as 2 into I'm sorry, this should be 2 into 10 to the power of 5, not 6. 2 into 10 to the power of 5 Newton per mm square. And also find the change in volume when pressure is, so I'll have to calculate delta V again. So for a stress of minus 100 Newton per mm square. Okay, so I've just directly taken the compressive load as minus here. Right, so let me just start with the Poisson's ratio formula. So Poisson's ratio will have 0.33, and now we know the relation between the elastic modulus and the rigidity modulus. So this is nothing but E is equal to 2G into 1 plus nu. Right, so if I substitute in this, I'll be having 2 into 10 to the power of 5 is equal to 2 into G, that is what we have to find, plus 1 plus 0.33. So here 2 and 2 will be cancelled. So rigidity modulus will be equal to 1 divided by 0.33. So which is nothing but G is equal to 75.18 gigapascal. Alright, so next, so we'll have a relationship between elastic modulus and the bulk modulus, so which is given by E is equal to 3K into 1 minus 2 nu. Right, so in this, if I substitute 2 into 10 to the power of 5 is equal to 3K into 1 minus 2 into 0.33. So which is nothing but, for this the K will be equal to 196.1 gigapascal. So now let me just write down the formula for K, which is nothing but the total compressive load or the total stress divided by the volumetric strain. So here the stress that we are having is minus 100 divided by the strain, so that is nothing but 196.1. I'll change from gigapascal to Newton per mm square, so that is nothing but 196.1 into 10 to the power of 3 Newton per mm square. So which is nothing but, so here I'm sorry, this is epsilon V, right? So volumetric strain will be given by this, so I've just cross multiplied. So here the volumetric strain will be nothing but 0.509 into 10 to the power of minus 3. Okay, so now volumetric strain is given by delta V divided by capital V. So here the delta V will be equal to epsilon V into capital V. Now epsilon V is given by, so this is minus 0.509 into 10 to the power of minus 3 into the volume. So since we have a cylinder, the volume will be equal to pi by 4 into d square. So d is nothing but 20. So we'll have 20 square into the length. Length is 750. So if I simplify this, the answer will be the volumetric, the delta V will be equal to minus 119.9 mm cube. So the minus represents here the size of the cylinder will be reduced. So this represents the reduction in size or the reduction in volume. Okay, so let me just stop here. Hopefully you've understood some concepts of strength of materials with these problems. See you in the next video. Happy learning.